Hey guys, so in today's video, let's learn how to draw Lewis dot structures. So I listed a few Lewis dot structures here. So first we need to know that all atoms in the periodic table want to get to noble gas configuration. So in the Lewis dot structure, we depict alkali metals and all these elements as follows. So for an alkali metal or hydrogen, you put the element symbol and one dot. Each dot represents an electron. Alkaline earth metals logically have 2, then 3, 4, 5, 6, 7, and noble gases have 8. Now these only signify the valence electrons. For example, sodium, even though it has 11 electrons, you're only going to depict it with 1 because it's really the valence electron that gets involved in all those reactions. The other 10 electrons just stay in there and do nothing. Now all noble gases, as noted here, have 2 s electrons and 6 p electrons. So it gives birth to the so-called octet rule. The octet rule states that in a Lewis dot structure, all elements must have exactly 8 electrons. Now, there's actually a lot of exceptions to this, plenty to be exact. Hydrogen and period 3 and beyond, in other words, row 3, 4, 5, 6, and 7, as well as hydrogen, can actually ignore the octet rule. I know, there's way too many exceptions to the octet rule, but group 2, period 2, that is, carbon, nitrogen, oxygen, and fluorine have to follow the rule. Actually, boron is another exception. Even though it's in period 2, boron can only make as much as 3 covalent bonds. So boron is really another exception to the octet rule. Here are some pictures of diatomic gases. Each bond here represents 2 electrons, so each chlorine here will have 8 valence electrons. Now I noted here that this diagram for oxygen is actually incorrect. Why is that? Well, that's because oxygen is actually paramagnetic. In other words, it's attracted to a magnet. Now, although it's way too fast, its molecules move way too fast in the gas phase to notice any effect by a magnet, if you condense it into liquid oxygen and then put a magnet at it, you'll see some tiny drops get attracted to it. And that's proof that oxygen is paramagnetic. If a substance is paramagnetic, like oxygen or iron, then they have unpaired electrons. If you look at the structure here, you'll see that all these electrons are in pairs of 2, right? But really in the real structure, oxygen will have unpaired electrons. Some of them won't have a buddy. So, the electrons actually cause a magnetic property. Electrons have something called a spin. It's either up spin or down spin. If there are more unpaired electrons, it means more of a specific spin, and therefore, well, more stronger attraction to magnets. However, if there are paired electrons, one will have the up spin and the other will have the down spin. So the 2 spins will cancel each other out, and therefore it won't be as attractive to a magnet. In fact, if there are paired electrons and only paired electrons, we say that the substance is diamagnetic. In other words, it thinks magnets are repulsive. They get repelled by the magnet. So that was a quick side lesson. Let's go back to Lewis dot structures. Now when you draw Lewis structures, we need to look for a few clues on how the dot structure will look like. Well, here are 2 clues to finding the skeleton of the Lewis dot structure. The least electronegative atom, except for hydrogen, will likely be the central atom. Now, why can't hydrogen be the central atom? Well, that's because it only has 1 bond. So, even if hydrogen wanted to be a central atom, it can't because there's only 1 bond. The halogen elements and oxygen are very rarely central atoms because they're so electronegative. Actually, fluorine is never the central atom because fluorine is the most electronegative atom. The only exception is hydrogen fluoride, but fluorine in general is almost never a central atom. So chlorine, bromine, iodine, and oxygen are very rarely central. Then we have to add the valence electrons. In other words, if you have, say, methane, each hydrogen, there are 4 of them, will have 1 electron, and we add the carbon's valence electrons, which are 4. So there will be a total of 8 electrons. That will be very useful in later when we graph it. Then number 2, add electrons if it's a polyatomic ion. More like a polyatomic anion. So all you have to do is add the charge to the number of valence electrons. So if it's, say, sulfate, then sulfur will have 6, and each oxygen will have 6 valence electrons. So a total of 30. But because sulfate's charge is a -2, it'll actually have 32 valence electrons. Same for cation. You subtract the electrons. So let's say an ammonium. In ammonium, nitrogen is 5, and each hydrogen has 1. So there will be a total of 9 theoretically, but because its charge is +1, it'll only have 8 valence electrons. Number 3, 2 electrons are 1 bond. The 2 electrons involved in a bond are called bonding pairs, and because of that, 2 electrons will be 1 bond. So for every bond you see on an atom, it'll mean that it has 2 electrons. And number 4, use the extra electrons that you didn't have to complete the octet for all the other atoms, so the non-central atoms. And number 5, put in lone pairs. So anything that didn't get bonded will be put as lone pairs. Now here are a few rules you need to follow about the octet. A. The structure is complete if all of the elements follow the octet. And B. If the central atom is boron, then the octet rule can be ignored as said earlier. If the central atom is period 3 to 7, you have permission to ignore the octet rule. And D. Period 2 must obey the octet rule, no matter what. There's really no exception. So let's start with something simple. Let's draw chloroform. Let's draw chloroform. So let's look at each element on the Pauling scale. Carbon is about 2.55 and chlorine is about 3.4. As you can see, carbon is less electronegative, so carbon is likely the central atom, which it is. Again, hydrogen is not considered because it can never be a central atom. So we get the basic idea that chloroform looks something like this, right? Chlorine, chlorine, and another chlorine. Now let's put it like this, so it's easier to see. So now let's add up the valence electrons. Chlorine is a halogen, so logically it'll have 7 valence electrons. Because there's 3 chlorines, 3 times 7, I'm pretty sure all of you know it's 21. Carbon, as a carbon group element, will have 4, and hydrogen will have 1. So we have a total of 26 valence electrons that we can use. Now does chloroform have a charge? I don't think so, I didn't put anything up there. So therefore we can use these 26 electrons to put in some bonds. So because carbon needs 4 bonds to follow the octet, right? 4 times 2 is 8. We put 1 bond for each. Seems simple enough. So carbon has already followed the octet. And because we have consumed 8 electrons in the process, that means we have 18 more electrons we can use. So because of that, we have to put them on the chlorine. So let's put 1, 2, 3, 4, 5, 6 electrons for each chlorine, right? Chlorine has to follow the octet rule here. So we put it like that. And there you have it, the complete Lewis dot structure of chloroform. Let's look at boron oxide this time. Now as you can see, I put in boron on purpose just to show you guys why boron gets to ignore the octet rule. So as you can see, boron is obviously the central atom. Oxygen is very electronegative and boron is a metalloid. Metalloids tend to be less electronegative than nonmetals, so it's simple logic that boron is most likely the less electronegative element. In fact, boron actually is. If you list the electronegativities here, you can very clearly see that boron is much less electronegative. So boron oxide should actually look something like this. So now let's add up our valence electrons. Boron is a group 13 element, so it will have 3 valence electrons. Because there's 2 of them, 2 times 3, all you know is 6. Oxygen is a chalcogen, in other words, an oxygen group element, so group 16. So they have 6 valence electrons. Because there's 3 of them, we have 18. Add them all up, I'm pretty sure you get 24. Okay, so we have 24 valence electrons we can spend on bonding and lone pairs. Now, do we have a charge? No, we do not have anything up here. So therefore, we have exactly 24 valence electrons. So let's put in some bonds. 1, 2, 3, right? 1, 2, 3. 2, 2, 2, 2, 2, 2. So minus 12, and we have 12 extra electrons you can spend. However, if you put the 12 electrons like this, which is actually true, you can see that boron actually ignores the octet rule. It only has 6 electrons when it's supposed to have 8. So this is the reason why boron gets to ignore the octet rule. The other elements have to follow the octet, so boron has no choice but to ignore it. Since we already used the 12 for lone pairs of oxygen, we have 0 leftover electrons, as you can see here. So this is some proof that boron has permission to ignore our octet rule. Now let's get into some anions. For instance, nitrate ion. Well, since nitrogen is less than electronegative, right? Nitrogen is about 3, and oxygen is about 3.5. So, therefore, nitrogen will be the central atom. Nitrate should look something like this, right? Perfectly logical. Now let's add up our valence electrons. Nitrogen has 5. 5 times 1 equals 5. Everybody knows that. Oxygen has 6. I'm pretty sure we have memorized it by now. 18. Add them up, you get 23. But remember, we have a charge here of 1 minus. So we add an extra electron. So we have 24 electrons you can spend on bonding and lone pairs. So let's get bonding. Nitrogen has this, right? But here's the issue. Nitrogen has to follow the octet rule. Here, nitrogen only has 3 bonds. So we're gonna have to resort to the double bond. A double bond is basically just 2 bonds. So 2 bonding pairs making 2 bonds. Let's just choose some random oxygen to the double bond. Any oxygen can be true, and we're going to talk about that in the next video when we talk about resonance structures. Anyway, so now we have our basic structure. Since oxygen has 4 electrons in our scenario, we need to put 4. Actually, we need to subtract the bonds first. 1, 2, 2, 2, and 2. That's 8, 16. And then we put in the lone pairs, 6 and the 6 and the 4. That makes 16. That's 0. So therefore, this is the structure of the nitrate ion. Wait, no, it isn't. Remember, we had this 1 minus charge from the start. And if you put it like this, some people would think, oh hey, nitrate's neutral. Wait a minute, like that. So we need to put in brackets and then signify this as an anion by putting this negative sign. So that's how you graph a polar atomic anion, for our case nitrate. Now let's draw a polar atomic cation, our case ammonium, as mentioned earlier. Well, because hydrogen isn't considered central, nitrogen is our only choice of the central atom. So ammonium will have a basic structure like this. Now I'm drawing everything in 2D so you can see everything better. Ammonium will have like a tetrahedral structure when drawn in 3D. So now let's add up our valence electrons. Nitrogen has 5, 5 times 1 equals 5. Hydrogen has 1, 1 times 4 equals 4. We have 9 electrons. Wait, no, we don't have 9 electrons. Remember this 1 plus charge, so we have to subtract 1. So we have 8 electrons that we can use in bonding and other stuff. Well, we only have, 4 bonds you can put in. Done. Well, we actually already consumed all 8 electrons. which is actually perfectly normal. Hydrogen doesn't produce lone pairs like here or anywhere else. But remember everybody, we have a cation. So we need to put it in brackets like that, and then put a plus. For our last example, let's draw xenon oxytetrafluoride. This is one of those stuff you don't see every day, a noble gas compound. Noble gases don't usually form compounds, and that's what makes xenon oxytetrafluoride special. It's one of the few noble gas compounds. So xenon here will be our central atom, right? Xenon has electronegativity of 2.2, oxygen 3.5, fluorine has an electronegativity of 4. So xenon goes in the center like that, and then put oxygen, fluorine, another fluorine, and the last fluorine. So now let's add some valence electrons up. Xenon as a noble gas will have 8. 8 times 1 is obviously 8. Oxygen, pretty sure I have it memorized by now, 6. 6 times 1 equals 6. Fluorine as a halogen will have 7. 7 times 4 equals 28. And add them all up and you get 42. So we have 42 electrons to spend on bonding. But if you skipped ahead a few more steps, you might say, hey, Ethan, this chemical is weird. Because if you put it like this and try to put bonds on all of them, then you might notice it breaks the octet rule, right? Since there's at least 10 electrons involved with xenon. Actually, you're allowed to break the octet rule at this point. Because remember, xenon's in period 5 of the periodic table. If you look up the periodic table, each and every single one of them will show xenon in the 5th period. So therefore, xenon actually has permission to ignore the octet. So because of that, we can actually put more than 4 bonds on xenon. So you can do this, 2, 2, 2, 2, 2, and 2, that makes 12. So we have 30 extra electrons left. So let's put them in for our lone pairs. 1, 2, 3, 4, 5, 6. Pretty sure you guys all know how to put lone pairs onto the octet now. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. And lastly, oxygen, 25, 26, 27, 28. And wait, we have 2 extra electrons. That's weird. Well, you see, sometimes we have no choice but to add even more electrons to a central atom. And because xenon has permission to break the octet rule, we can just do it how much as we want. Because you have 2 extra electrons, and oxygen, fluorine, and every other fluorine has their octet satisfied, that means these 2 electrons are going to have to go on to xenon. So let's put in the lone pair right here. So now we subtract our 2, and we get 0 leftover electrons. So there you have it everybody. How to draw Lewis dot structures. Thanks for watching and see you in our next AP chemistry videos. Bye!